Take a moment, close your eyes, and imagine looking up at the night sky. Truly looking. Each point of light you see isn't just a star, but a time capsule. You're not seeing them as they are, but as they were, thousands, sometimes millions, or even billions of years ago. Light, though fast, takes time to travel. And so, as we gaze out into the cosmos, we're not seeing the present. We're peering deep into the past. But how far can we truly see? Where does that view end? This limit, the outermost boundary of what we can observe, is called the observable universe. It's not a wall or a border in the physical sense. Rather, it's the edge of what light has had time to reach us from since the Big Bang, around 13.8 billion years ago. But due to the expansion of space itself, that light has traveled much farther than 13.8 billion light years. In fact, the furthest observable regions now lie about 46 billion light years away in every direction. This gives the observable universe a diameter of 92 billion light years, an immense sphere surrounding us like a cosmic snow globe. Yet even that number is misleading, because the universe is not confined to what we can see. It's like standing in the middle of a vast ocean, only able to see as far as the horizon, but knowing intuitively, deeply, that more lies beyond. That's the paradox of the observable universe. The edge is not the end of existence, but the end of visibility. Beyond that horizon, countless galaxies may thrive, untouched by our gaze, forever out of reach, not because they don't exist, but because their light hasn't arrived. And here's a deeper thought. Because the universe expands faster than light can travel at great distances, some galaxies we see now have already disappeared beyond that horizon. We are watching ghosts, ancient light from worlds that will never interact with us again. Still, the edge invites wonder. What lies beyond this cosmic curtain? If we could step past it, would we find more stars, stranger physics, or even entirely new dimensions? Let's journey further into the very fabric of space itself and how it continues to stretch, quietly, endlessly. Imagine a night sky frozen in place, stars unmoving, galaxies quietly suspended in the stillness of a timeless void. For centuries, this was our assumption. The universe, we thought, was eternal and unchanging, a vast static dome over our heads. But then, something extraordinary happened. We started listening to the light. When astronomer Edwin Hubble examined the light from distant galaxies in the 1920s, he discovered something unexpected. That light wasn't just dimmed or scattered, it was red-shifted. The farther away a galaxy was, the more its light shifted toward the red end of the spectrum. This redshift wasn't caused by motion through space, like a car driving away from you, but by the stretching of space itself. The universe was expanding. But what does it mean for space to expand? Picture the universe not as a container with galaxies inside, but as a flexible fabric, like the surface of an inflating balloon. Galaxies are dots on that surface, not flying outward on their own, but carried apart as the balloon swells. Space isn't a backdrop, it's an active player. It stretches, it evolves, it grows, and it's not slowing down. In fact, the expansion of the universe is accelerating, driven by an elusive force known as dark energy. Over cosmic timescales, this expansion means that galaxies we can see today will eventually fade beyond our observational reach. The light they emit will stretch so thin that it never reaches us. We won't see them go. We'll just slowly forget they were ever there. The most haunting part. Future astronomers, living in a time long after this age of visibility, may look out and see nothing but darkness. The expanding fabric of space will have erased the cosmic record, leaving behind only local galaxies, an island in a seemingly empty sea. And so, the expansion of space isn't just a scientific fact. It's a profound reflection on impermanence. The cosmos itself is teaching us that nothing, not even the universe as we know it, stays the same. But if space is expanding, stretching like a living thing, what of time? Does it too bend, ripple, and shift as we move farther into the universe? Let's drift now into the enigma of time itself. From the moment we're born, time begins to shape our lives. School bells ringing, birthdays passing, deadlines creeping closer. We live in time, we breathe it, and we trust that every second that ticks away is the same for everyone, everywhere. But what if that's an illusion? What if time isn't a universal metronome, but a strange, shifting fabric, one that bends, slows, or even stops altogether? Albert Einstein shattered our common-sense view of time when he introduced the theory of relativity. He showed that time is not separate from space, but intertwined with it, forming a single entity, space-time. According to his equations, time moves more slowly the closer you are to a massive object, and the faster you travel, the more time slows for you. This isn't science fiction. It's been confirmed by precise clocks flown on airplanes and satellites. Time is relative, but the effects grow more bizarre as we stretch deeper into the universe. Near the edge of a black hole, gravity is so intense that time dilates dramatically. To an outside observer, a falling object appears to freeze at the event horizon, as if time itself has stopped. For the object falling in, however, time seems to flow normally. Two realities side by side, each experiencing time differently. This leads to a haunting implication. If time can flow at different rates depending on your position and motion, what does that say about the nature of the present? Is there even a single, shared now? Some physicists argue that the past, present, and future all exist simultaneously, like slices of a loaf of bread. We only perceive time as passing because our consciousness moves through those slices in order, like a needle on a record. Every moment still exists, somewhere. And if that's true, then every memory you've ever had, every future you'll ever see, may already be written in the cosmic ledger, waiting to be read. The universe becomes less like a movie playing in real time, and more like a book already written, waiting for the pages to be turned. So if time isn't a flowing stream but a sprawling terrain, then what happens at the places where that terrain collapses under its own weight? Let's descend now into the strangest of valleys, into the deep, dark mystery of black holes. Picture for a moment a place so extreme that the very fabric of space and time is pulled to its breaking point. A place where light itself, the fastest thing in the universe, cannot escape. Not because something is blocking it, but because the rules of space no longer allow escape. This is no fantasy. This is a black hole, one of the most mysterious and terrifying objects in the universe. Black holes are born from death. When a massive star exhausts its nuclear fuel, its internal pressure can no longer resist the pull of gravity. The star collapses in on itself, shrinking smaller and smaller until all of its mass is crushed into an unimaginably dense point called a singularity. Around this point forms the event horizon, the boundary beyond which nothing can return. Not a particle, not a photon, not even time itself. Once you cross it, you are cut off from the rest of the universe. But what lies inside? Here, physics loses its footing. Gravity becomes infinite, space and time twist beyond recognition, and the laws that govern everything we know, from atoms to galaxies, fall apart. Some believe black holes are the key to a new kind of physics, a place where quantum mechanics and general relativity must finally come together. Others wonder whether information, the fundamental fingerprint of matter, is lost forever when something falls in. That question, known as the black hole information paradox, remains one of the deepest puzzles in theoretical physics. And then there's the speculation. Could black holes be bridges to other regions of the universe, or even to other universes entirely? Some solutions to Einstein's equations hint at the possibility of wormholes hidden within black holes, acting as tunnels through space-time. But such ideas remain deeply theoretical, and any traveler attempting to explore such a path would likely be shredded by tidal forces long before reaching the singularity. Still, black holes captivate us not just because they are destructive, but because they guard secrets. Secrets of matter, of time, and perhaps even of creation itself. To approach one is to approach the unknown, a silent abyss with answers written just beyond the veil. And if black holes might hold passageways, could there be actual tunnels through the universe, ones that fold space itself? Let's now explore that tantalizing possibility. The wormhole. Imagine walking into one room and stepping out the other side of the galaxy. No rocket, no warp drive, no need to cross the endless void, just a passage through space folded in on itself. This is the promise of a wormhole, one of the most tantalizing ideas ever to emerge from the strange depths of physics. Wormholes, also called Einstein-Rosen bridges, are theoretical constructs born from the equations of general relativity. In simple terms, they represent tunnels connecting two separate points in space-time. One end could open near Earth, the other beside a distant star, or even in another galaxy altogether. What's more, these tunnels might not just connect space to space, but also time to time. One end could exist in the present, the other in the far future, or the distant past. The concept stretches our minds. It suggests that the universe, vast as it is, might have hidden paths, cosmic shortcuts veiled behind mathematics and mystery. But as with many elegant theories, there are complications. Wormholes, if they exist, may be wildly unstable. The tiniest disturbance, a stray particle, a flicker of energy, could collapse the tunnel in an instant. Some theorists propose that exotic matter, with negative energy density, might be required to keep them open. But exotic matter remains so far a speculative ingredient, more imagination than observation. And yet, the idea persists, not just because it fuels science fiction dreams of instant space travel, but because it challenges our sense of separation. If wormholes are real, then distance, and even time itself, could become navigable in ways we've never imagined. Entire galaxies could be within reach. The barriers between then and now might blur. Some physicists even suggest that wormholes might be lurking inside black holes or hidden in the quantum foam, the seething substructure of space-time at the smallest scales. Others wonder whether wormholes have already formed, only they're too small or too distant to detect. Whether they're practical travel corridors or mere mathematical artifacts, wormholes provoke the question: is the universe more connected than it seems? And if shortcuts through space and time are possible, what if our entire universe is just one thread in a vast cosmic weave, one bubble in an endless sea? Let's step now into the strange and shifting idea of the multiverse. Close your eyes and imagine our entire universe, everything we know, every galaxy, star, and particle, as just a single bubble floating in a vast, infinite sea. Now imagine that all around us are other bubbles, each containing a universe of its own, with its own laws, its own beginnings, and perhaps even its own forms of life. This is the mind-bending idea of the multiverse, the notion that our universe is not the universe, but merely one of countless others. The idea of a multiverse doesn't come from fantasy or science fiction, though it has inspired plenty of both. It emerges from serious physics. One source is inflation theory, the idea that in the earliest fractions of a second after the Big Bang, space expanded at an astonishing rate, faster than the speed of light. In some models, this inflation never stopped. While our region of space slowed and cooled into the universe we see today, other regions kept inflating, birthing new universes in a never-ending cascade. Like bubbles forming in boiling water, each universe arises from the same seething chaos but unfolds differently. Quantum mechanics adds another layer to the mystery. In the strange world of the quantum, particles exist in many states at once until observed. Some interpretations suggest that every time a quantum choice is made, every time an atom jumps one way instead of another, a new branch of reality is created. This many worlds view imagines an infinite number of parallel timelines, each containing a different version of you, of Earth, of everything. But here's the challenge. We can't see these other universes. We can't visit them. Their light will never reach us. So how can we know they exist? Are they real, or just reflections of mathematical imagination? This is the paradox of the multiverse. It offers sweeping answers to questions about fine-tuning, about choice and chance, but it teeters on the edge of science and philosophy. Still, the possibility lingers, that our universe is just one note in a grand symphony, and somewhere, maybe, there's a version of you that never turned away from a path, never lost an opportunity, never even heard of this one. Let's turn now from the cosmic scale to the microscopic, to the shimmering, unpredictable dance of particles that underpins everything we call real. Welcome to the quantum world. Beneath everything you see, beneath your hands, your breath, your thoughts, lies a world that obeys rules more surreal than anything dreamed of in myth or philosophy. It is the quantum world where certainty dissolves and what we think of as reality begins to flicker and blur. Here, particles do not have fixed positions, and cause and effect are no longer ironclad. At the very heart of existence lies uncertainty, not as a mistake or a gap in our understanding, but as a fundamental feature of nature itself. In classical physics, objects are predictable. A ball thrown into the air follows a clear path. But on the quantum scale, particles like electrons or photons don't behave like tiny billiard balls. Instead, they exist in a haze of probability, a cloud of possibilities. Until we observe or measure them, they don't have a definite position or momentum. They exist in multiple potential states at once. It is only in the act of measurement, of interaction, that one reality is selected and the rest vanish. This strange behavior was first captured in the famous double-slit experiment. When not observed, particles behave like waves, passing through both slits and creating interference patterns. But when watched, when measured, they suddenly act like particles, going through one slit or the other. The mere act of observation changes the outcome. It's as though the universe waits for someone to look before deciding what to be. The implications are unsettling. Does observation shape reality? Is the act of measurement an act of creation? Some interpretations suggest that consciousness might play a role in collapsing the quantum wave function, a bold and controversial idea that blurs the line between physics and philosophy. Others argue the universe simply measures itself through interaction, requiring no conscious observer at all. And then there's the question of determinism. If outcomes are based on probabilities, not certainties, then the future is not set in stone. Every particle interaction introduces chance. Perhaps our world, our choices, and even our very existence are the products of a vast quantum lottery, a dance of randomness that gave rise to order. But if everything flickers with uncertainty now, what about the beginning? Was there a moment before probability, before time and space, when something arose from nothing at all? Let's turn to that primordial silence and the mystery of how everything began. Take a moment to imagine absolute nothingness, not a black void or an empty room, but the complete absence of space, time, matter, and even the rules that govern them. No before, no after, no up or down, no particles, no light, just nothing. And now consider the most bewildering question of all. How could something, everything, have sprung from that? For centuries, the idea that the universe began from nothing was both unsettling and profound. But modern physics has given the concept a curious twist. In the realm of quantum mechanics, even nothing isn't truly nothing. The so-called quantum vacuum, the lowest possible energy state, is not a barren void. Instead, it teems with restless activity. Particles and antiparticles spontaneously flicker into existence, collide, and vanish again in a haze of uncertainty. This phenomenon, known as quantum fluctuation, reveals that even emptiness is unstable. Some cosmologists propose that our universe may have begun as such a fluctuation, a temporary blip in the quantum fabric that somehow inflated into everything we now know. According to this view, the Big Bang was not the creation of something from a true nothing, but a transformation, a spark ignited within a sea of hidden possibility. Time and space may have unfurled from this seed, expanding faster than light in a cosmic growth spurt known as inflation. It's a notion that rewrites the very idea of creation. If nothing naturally gives rise to something, because that's what nothingness does, then perhaps the existence of the universe isn't surprising at all. Perhaps the real mystery isn't why there is something rather than nothing, but why that something gave rise to order, to stars, to consciousness, to us. And still we wonder, was the Big Bang truly the beginning, or was it simply a turning point in a larger cycle? Could the universe collapse and be born again? Could there have been other beginnings, other bangs in other bubbles? From nothing, a cosmos. From silence, a symphony. But every story has not only a beginning, it has a direction. So now that we've glimpsed where it all began, let's gaze forward toward the far horizon of time and ask, how will it all end? Every beginning implies an end, and the universe, as grand and eternal as it may seem, is no exception. But contrary to the fiery cataclysms often imagined in myth or fiction, many scientists believe the cosmos may not end in a blaze, but in a long, slow fading. Not with a bang, but with a whisper so quiet, so gradual, that even time itself seems to lose meaning. This quiet unraveling is known as heat death, a concept rooted in the laws of thermodynamics. As the universe continues to expand, galaxies grow more distant, stars exhaust their fuel, and black holes slowly evaporate. Over trillions of years, matter decays, light fades, and temperature drifts toward absolute zero. Eventually, energy becomes so evenly distributed that no differences remain, and without differences, no work can be done. No stars, no motion, no life. It's a vision of the cosmos drained of contrast, of purpose, a place where every atom is alone, and even time becomes irrelevant because nothing changes anymore. Entropy, the measure of disorder, reaches its maximum. The universe, once so vibrant, slips into a frozen stillness. And yet, even in this desolate future, possibility lingers. Some cosmological models propose that the universe could eventually reverse course, contracting in a big crunch, collapsing in on itself until another bang ignites a new cycle of creation. Others suggest the idea of a big bounce, a rhythmic universe that expands and contracts forever, pulsing like a cosmic heartbeat. And then there are those who wonder whether even heat death is truly the end. In the ever-churning quantum foam, could a new fluctuation spark another universe, just as ours may have once arisen from nothing? What lies beyond the edge of time? Perhaps a rebirth, or perhaps a silence so profound that even questions dissolve. And yet, the very act of imagining this future, the thought that stirs in us now, is itself a rebellion against finality. We are the universe thinking about its own death, dreaming of its possible rebirth. But before we go too far into these future shadows, another question lingers behind us. In all the vastness we've traversed, with all its galaxies and mysteries, something feels missing, something personal. In this infinite stage, is there anyone else? Let us turn now to the silence that surrounds us, and the paradox of why, in a cosmos so full of stars, we seem so utterly alone. On a clear night, if you gaze long enough at the stars, a question naturally rises. With so many of them shining out there, trillions of stars, many with planets, why haven't we found anyone else? Where are the signs, the signals, the visitations? This simple yet profound question lies at the heart of one of the most unsettling mysteries in science, the Fermi paradox. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" the paradox highlights a striking contradiction. Given the age and size of the universe, intelligent life should not only exist elsewhere, but it should be widespread. If life arises naturally, If intelligence evolves as it has on Earth, then we should be hearing from others, detecting them, perhaps even visited by them. And yet, the cosmos is silent. There's no shortage of possible explanations. Some scientists propose the idea of a great filter, a hurdle so difficult that most civilizations never make it past a certain point. Maybe life itself is incredibly rare, or maybe intelligent life tends to self-destruct, collapsing under the weight of its own technology, its own ambition. Wars, environmental collapse, artificial intelligence gone awry. Any number of endings could explain the silence. Others suggest that advanced civilizations might deliberately hide, either for safety or out of disinterest. Perhaps they are watching us as we would observe animals in a sanctuary, choosing not to interfere. Some even propose the idea of a cosmic quarantine, where immature civilizations like ours are isolated until we are ready, if such readiness ever comes. And still, it's possible that we're simply not listening in the right way. Perhaps alien life doesn't use radio signals. Perhaps their methods of communication are so far beyond us, so subtle or strange that we don't even recognize them as messages. We may be surrounded by signs. We just lack the ears to hear. Or maybe, and this is the most haunting possibility of all, we truly are alone. A fluke in the cosmic lottery. A rare spark in a universe mostly dark. But if we are alone, then something extraordinary is also true. We are the consciousness of the universe, the part that looks back and wonders. And that brings us to an even deeper mystery. Not what's out there, but what's in here. Let's now explore the enigma of consciousness and how matter becomes aware. As you lie still, listening to these words, something remarkable is happening. You're not just absorbing information, you're aware that you are. You are conscious, experiencing thoughts, feelings, and memories in a rich, continuous stream. But what is this thing we call consciousness? Where does it come from, and why does it exist at all? For all our advances in science, consciousness remains one of the most profound and persistent mysteries. Neuroscience can map the brain in exquisite detail, tracing neural pathways, firing patterns, and chemical interactions. But even the most detailed scan cannot explain the feeling of being. Why should electrical activity in a lump of grey matter produce the warmth of love, the sting of regret, the colour blue, or the idea of infinity? How does matter, physical, measurable, and impersonal, give rise to subjective experience? Some scientists argue that consciousness is an emergent property of complex computation. When matter reaches a certain level of organization, as it has in the human brain, awareness simply emerges, like a flame from friction. Others suggest that consciousness may not be a byproduct of the universe, but a fundamental part of it, woven into the very fabric of reality, like space and time. This is known as panpsychism, the idea that some form of consciousness pervades all things, even in the smallest particles. Quantum physics, too, has entered the discussion, with theories suggesting that consciousness might play a role in collapsing the wave function, the idea that observation itself shapes reality. While controversial and far from proven, these ideas suggest a universe where the act of perception is not passive, but participatory, where reality, in some sense, requires a witness. And if that's true, then we, as conscious beings, are not just residents of the universe. We are active participants in its unfolding. The universe, through us, becomes aware of itself. Through our stories, our questions, our quiet moments of reflection, it gazes back across time and space and wonders. But if consciousness plays a role in shaping our experience, perhaps it also plays a role in shaping the universe itself. Could the world be the way it is because we are here to observe it? Let's explore this possibility next, through the lens of the anthropic principle. As we gaze out into the cosmos, at galaxies spun from light, stars born from dust, and atoms forged in ancient fire, we're struck by a strange truth. The universe seems just right. The laws of physics, the constants of nature, the balance between forces, all of them appear exquisitely tuned to allow for life. And not just life, but intelligent, conscious life that can ponder its own existence. Why is the universe so precisely calibrated for us to be here? This is the question at the heart of the anthropic principle. At first glance, it feels circular, almost trivial. Of course, the universe allows life. We're here to notice it. But beneath that simplicity lies a much deeper, more unsettling mystery. What if the universe could have been different? What if gravity were slightly stronger, or the charge of the electron slightly different? In many of those altered versions, stars wouldn't form. Chemistry wouldn't exist. Life, as we know it, would be impossible. So, why does it work so perfectly? One interpretation is that we're simply lucky, the cosmic equivalent of winning the most improbable lottery imaginable. Another suggests we aren't special at all. If there are countless universes, each with different physical laws, then most of them would be sterile. In a multiverse full of lifeless variations, we just happen to live in the rare one that works, because only such a universe could host beings capable of asking the question. Then there are those who see purpose in the precision. Perhaps the universe isn't an accident, but part of a deeper design. Some invoke theology or metaphysics, others a yet undiscovered principle of nature that requires things to unfold this way. Maybe consciousness, or life itself, is more than an emergent property. Maybe it's a destiny. And yet, we are left in a delicate position, wondering whether we are at the center of meaning or merely the edge of randomness. Either way, the fact remains. The universe seems improbably perfect, and we are here, witnessing it. But if the universe is so finely tuned, could there be a deeper logic underneath it all, some hidden order behind the veil? Let's now peer into the structure beneath reality itself and explore the strange idea that everything we see may be a cosmic illusion. We move through a world of depth, up and down, near and far, wrapped in the comforting solidity of 3 dimensions. Mountains rise, oceans curve, stars recede into the infinite black. But what if this familiar, spatial reality is not what it seems? What if the universe, in all its apparent depth, is actually a kind of illusion, a projection cast from a surface we cannot see? This is the astonishing idea behind the holographic principle. Born from the efforts to unite quantum mechanics and gravity, this theory proposes that everything we experience, from particles to planets, from space to time itself, may be encoded on a distant, 2-dimensional boundary. Much like a hologram, etched on a flat surface that appears to hold depth when illuminated, the universe might be a 3-dimensional expression of hidden, lower-dimensional information. It began with black holes. Physicists discovered that the amount of information a black hole can contain, its entropy, doesn't scale with its volume, as one might expect, but with its surface area. This hinted at something profound. Perhaps the fundamental bits of reality don't reside inside space, but on its edges. If this is true for black holes, could it be true for the universe itself? In this view, our reality, everything we touch, see, and think, emerges from quantum data encoded on a vast, far-off surface, like a cosmic hard drive projecting the illusion of a world. It's a wild idea, yet some versions of string theory support it, and certain aspects of quantum field theory seem to demand it. Gravity, under this model, is not fundamental, but an emergent effect, a shadow cast by deeper quantum truths. Strangely, this modern theory echoes ancient ideas, from Plato's cave, where people mistake shadows for reality, to mystical traditions that speak of the world as a veil or dream. Perhaps, as science loops back on itself, it finds poetry at the edges. And if our world is a projection, what's doing the projecting? Where is the source? What mechanisms lie behind the screen? Let's take one final turn inward, beyond physics, beyond even holograms, and ask a question that haunts both science and science fiction. What if all of this is code? Could we be living inside a simulation? What if everything you've ever known, your memories, your dreams, your sense of self, is part of a vast, intricate program? What if the stars you gaze at, the time you feel passing, and the very laws of physics themselves are all lines of code running on some unfathomable processor? This is the unsettling, fascinating proposition known as the simulation hypothesis. The idea that our entire universe might be an artificial construct, a simulated reality created by a higher intelligence. It sounds like science fiction, but serious thinkers have taken the idea seriously. Philosopher Nick Bostrom famously argued that if civilizations can eventually create realistic simulations of conscious beings, and if they choose to do so, then statistically, most minds like ours would be simulated rather than real. The logic is cold but compelling. If it's possible to simulate a universe indistinguishable from reality, and if even one advanced civilization does so, then the number of simulated realities could vastly outnumber the one original, base reality. And if that's the case, how would we know? The simulation could be flawless. The laws of physics, the constants of nature, even our own biology could simply be part of the code. Glitches, anomalies in our physical world, unexplained quantum phenomena, or mathematical patterns might be the only hints, though even those could be intentional design features. But beyond the question of whether it's true lies a deeper unease. If we're in a simulation, what does that mean for free will? Are our choices genuine or predetermined by some hidden algorithm? If suffering can be simulated, does it matter less or more? And who or what is the programmer? A godlike entity, a future civilization, a curious intelligence experimenting with reality? The idea stretches philosophy, physics, and theology until their lines begin to blur. Some see it as liberating, a new mythology for a digital age. Others see it as a modern echo of ancient doubts. The suspicion that what we experience isn't the full truth, that we are shadows on a wall, watching a play we didn't write. And yet, even if we are simulations, even if the stars are just pixels and time a looped function, the wonder we feel is real. The awe, the curiosity, the love, the pain, they are ours. So let us pause now and take one final look, beyond the illusions, the questions, the boundaries, as we arrive at the very edge of the observable universe. And now we arrive, not with answers, but with awe. After a journey that has taken us through the collapse of stars, the flicker of quantum particles, and the far-flung possibility of alternate worlds, we find ourselves here, at the edge. But this edge is not a cliff in space or a border in time. It is something far more intimate. It is the limit of what we can see, know, and perhaps even imagine. The edge of the observable universe is often described as a physical boundary, some invisible shell around us, 46 billion light-years away in every direction. But this edge is not a wall, it's a horizon. A reflection not of where the universe ends, but of where our perception does. It marks the frontier of light's reach, the border where time has not yet allowed photons to arrive. Beyond it may lie more galaxies, more stars, more wonders than we can fathom. But for now, they remain hidden, not by distance alone, but by the fundamental constraints of space, time, and light. And yet, this is not the only edge we face. The cosmos offers many kinds of boundaries, the edge of what our tools can detect, of what our minds can comprehend, of what our language can describe. Every discovery shifts that edge outward, but never erases it entirely. There is always something just beyond, another layer, another mystery, another why. That is the beauty of the journey. The edge is not a place to stop, but a place to begin again. The threshold where curiosity stands poised to leap. No matter how far we reach, no matter how deep we peer, there will always be more. And that more is not a failure of knowledge, but its driving force. So take a moment to breathe, to feel the quiet magnitude of this moment. You are a brief flicker in an ancient unfolding, a thread of awareness woven into a vast, unknowable tapestry. And though your life is small compared to the stars, it is no less miraculous. Because you are here, you are thinking, You are wondering. And the edge? The edge is not the end. It is where the next question waits.